Another MEscope webinar. My name is Mark Richardson, the marketing manager with Vibrant Technology, and today I'm joined by a few other family members. Sean Richardson and Mark Sr. are joining us today. And the topic of today's webinar is getting started with, well, no, it's not getting started. It's Video ODS cell phone shootout, excuse me. Today we're gonna look at both the iOS and Android phones. Obviously, iOS is the dominant phone here in the United States. It's over like 60%, I think, in North America. But you look globally, and Android sells 3 out of 4 phones, so 75% market share for Android. So obviously, we want to showcase what both these phones can do with our software. So we came up with this webinar here to do a little shootout and test each phone and see what the results look like, and go through a little bit also on how you set up both phones, so that if you are using one or the other, you kind of have a little tutorial here on some of the setup features for utilizing Video ODS. A couple housekeeping items. We will be recording this, so anytime you want to go back and take a look at this, we will have this out on our YouTube site here probably beginning of next week. We'll get that posted. You also will, I believe, receive a recording of the webinar from GoToWebinar, so you'll get that in your inbox as well. If you do have questions, we will have everybody on mute until the end of the webinar, and then you can type in your questions into the GoToWebinar dialog box there on the right-hand side of your screen, and we'll try and get your questions answered at the tail end of today's webinar. With that, let me hand things over to Sean, and we will get started.
Sounds good. Thanks, Mark. Good morning. Yeah, we've done a bunch of these, or a number of these before, using the iPhone, kind of like Mark mentioned, and that's kind of been our standard. But we've expanded a little bit, and we're trying to cover the different options that you might have, and determine, the accuracy of the phones versus each other. This time, what we've done is we've added the Google Pixel Pro, which Mark mentioned is on the Android platform, but is a Google phone. In a lot of ways, when you look at the technical specifications, very similar to the iPhone. The options, as far as the video options go, using HD, you're going to have 30 and 60 frames per second. 4K, you'll have 24, 30, and 60 frames per second. And then both phones offer slow-mo, which goes in 1080p HD, in offerings of 120 frames per second and 240 frames per second. Now, one interesting thing that we came across when we did a little bit of deep dive into this is a 240 frames per second option on the Google is a true 240 frames per second. So you're going to get that, which is going to get you, a frequency span of 7,200 RPMs. So we'll talk more about that. But interestingly enough, in the iPhone, it has a video optimization thing that you can't turn off on the 240 frames per second. So it's optimizing video quality over the actual frame rate. So you'll get variability in there. And a lot of times, if you go back and you actually look into the file itself, you'll see 157.5 frames per second, 190 frames per second, and not true 240. And it's variable across the span. So for me, after we've done this shootout, I'm eliminating, at least for our use on our side, the 240 frames per second from the iPhone, just for the simple fact that you can't, it just doesn't have a consistent frame rate, and in a lot of cases, it's not a true 240. But the Google Pixel, it does offer true 240 frames per second. So something interesting right there, just to get us started with. This video that we'll just let run really quickly. It talks about some editing that where you can find the slow-mo tab. That I'm working on a Google Pixel tutorial, and I'll have that out beginning of next week. But the functionality is very similar. You go to the video feature, it's got all your standard video, which is your 24, 30, and 60 frames per second, and then it has a slow-mo tab that you slide to also and make your selection. But this video that'll play is the actual iPhone video. But iPhone has selection on the top. The Pixel does the same way, and then it has a slow-mo tab. But the way you cycle through the different options is that same way. All right. So consider some considerations anytime you're taking any sort of video, but it applies to both phones, and the considerations that we had in this scenario here. Obviously HD versus 4K. HD is your 1080p, which is 1920 pixels by 1080 pixels, which is the 1080p. 4K is 4 times that. And if you've got something that you can deal with in a lower frequency range, a lower RPM range, especially, 4K is much sharper. You get better resolution, more accuracy. Now we'll do the shootout, and you're going to see that even, you know, between 120 and 60, like the data is very, very, very similar. But for your visually or just pure accuracy perspective, if you're, you know, working with magnitudes and things like that, your 4K is going to give your best option. Things to consider out of there, and what your frame rates get you as far as usual frequency span. We talked about on the low end, 30 frames per second is going to get you 900 RPMs or 15 hertz, 60 frames, 1800 RPMs, and then all the way up to 240, which is 7200 RPMs and 120 hertz of a frequency span there. The biggest thing, again, we talked about the iPhone, you know, you kind of stuck at 120, but the will take you all the way up to 240. And then you can actually get further range than that. We won't go into it today, but we have something that, especially for rotating, reciprocating machinery, where you're going to have multiple orders. We'll unalias the data, so that what it'll do is it'll take the alias data that folds back on itself, unwrap it. So essentially what you'll get is double the usable span. So, you know, 7,200 RPMs on here, you know, becomes over 14,000 RPMs. That's usable from a looking at orders perspective. Time considerations, all the videos that you'll see today were done with 10 seconds of video. So the resolution is 6 RPMs or 1/10 of a hertz. You can go longer, obviously, and that's going to increase your resolution and get the number of RPMs or the hertz value per sample smaller. But for this, we did 10 seconds per. And what you would typically do is you record 15 or 16 seconds worth of data and just grab the middle 10 seconds. And you'll see this in the videos we get further along. But that's really the best way to do it. So I would suggest taking 5 or 6 seconds over what you would normally, what you'd want to use your end value goal, and then take the middle section and use that when you're processing the video. Simple phone setup, and again, you're going to see this. We're using this rotating machine trainer with some unbalance in it in the rotors. Really what you want to do majority of the time, depending on the alignment of the video, but you want to go there and you want to put it in the horizontal view. And you want to really maximize the structure that you're taking a video of in the viewing window. So without using a zoom function, you can use the zoom functionality in the phone. It works fine. It changes the resolution slightly, but it works fine for what you're trying to do. But maximize the structure of the viewing window so you can really maximize the number of pixels that are utilized when you're processing the video. And then another suggestion, we just use a cheap tripod from Amazon, but it really changes, you know, the stability as far as, like, you know, any sort of natural vibration from your hands or movement or anything like that. It gets rid of that. So you set it on there, you can hit the start button, or you can use a Bluetooth trigger if you want. Start it, let it run for the, you know, duration that you're looking for, and then stop it again. But it's stable the entire time in between there. Yeah, so that would be the start, and we'll stop there. Simple. The iPhone does this, and for the slow-mo, and the Google Pixel does as well. Again, I only have the Google Pixel video here, and you actually do the opposite of what you do for the iPhone with the Pixel. But in the iPhone, what happens is when you have a slow-mo video, kind of one of its cinematic features is it'll do full speed playback, and then it'll get to a middle section where it's got a much slowed down playback, so you can actually look at the slow motion, and then at the tail end it'll speed up again. With the iPhone, what you want to do is you want to take that cinematic playback section out of the middle completely. So you'll see in this video, you grab the slider bars, you slide them all the way to the right, and then you save that as your edit, and then you have just the true raw video of 120 frames per second or 240. It's not going to be a true 240, but it would be the same thing. With the Google, you actually want to take the full speed playback section out of it to the right and the left. So you just expand it. So it's just the slow-mo section, which is, again, it's the opposite of the iPhone, but it's what you do. But I'll have this in a tutorial. We'll make it available on the website to everybody who wants to see it for both phones when we're done with this here. But you'd be able to see on the video here with the iPhone, you would go to that settings, and then it has this section in the middle where it's the slow-mo. You just slide it all the way to the right. You would get rid of it, and then you would just save it at the top. And again, the Google is just the opposite of that. Some other things that we're not going to really cover today, but I'll have it in the video and you can check it out. A lot of people will take videos on what I would call an unstable platform, meaning something where the ground or the platform where the video has actually been taken from is shaking. Could be, you know, at a scaffolding in a paper mill, you could be on a ship, something like that, where dynamically the camera or the phone itself is moving. One of the things that we offer within the software is to remove background motion. And so essentially what you would do is you would select a point or group of points that you know are fixed, which means they're not moving at all. And then the calculation will take the vibration data, the vibration parameters from those fixed points, and then remove that data from the entire data set, which would take your ambient movement or your general motion that's affecting the phone out of the video. So you just get the true motion of the structure that you're videoing. And then another thing too, go into it just a little bit, we do spectrum averaging, windowing and things like that, just to clean up the data, make your peaks pop a little bit more. And again, a lot of the stuff is covered in other videos, but this is here so that you can take a look at it and go from there. And then obviously you can do ODS FRFs and cross spectrum, integrate and differentiate the data to, you know, get from displacement to velocity to acceleration and back and forth from there. But lots of things to cover here. So exciting, I'm going to get into it. We'll do a comparison between the videos of both phones at the different frame rates and comparisons and MAC value calculations, and really kind of make our determination at the end as to which we believe is more accurate, but the data will speak for itself. So with that, and then the unwrap machine orders, but we're not going to do that today. But with that, I'm going to pass it over to my dad, and we'll get into actual data analysis here. All right, how do I do this? All right, there we go.
Okay. Everyone can see my screen, hopefully.
Yep.
Yep.
Okay, the first thing I'm going to do is just show you the data that I have stored on my computer, the projects and the videos that Sean and I recorded last week with the two different cell phones. So here are the iPhone videos, the raw videos, 60 hertz. I like to use the word hertz because being a guy who used accelerometers forever and multi-channel data acquisition, that is the sample rate of the video. You know, normally you use the term frames per second. So when you think about videos, each frame is like a sample of data taken from an accelerometer or with the camera. And of course, the camera is recording a whole picture with each frame of data. So you can think of that as having a whole bunch of accelerometers all over the surface of whatever you're recording the video with. And the recording speed is 60 hertz, 120 hertz, 240 hertz. And then here are the three videos from the Pixel, or the I want to say Google phone.
Android.
Android, yeah, there we go. 60, 120, and 240. Google uses the extension MP4, which is a standard video format. Apple calls it a MOV, a movie. Well, let's just take a look. I'll just double click on one of these and we'll look at the raw video. And there's even recording of sound there. So this is what the camera actually recorded. And you can see a little bit of motion in the rotors. The rotors, if you look carefully, that we put a couple of unbalanced screws into the rotors just to make the machine vibrate a little better. You can see that we got 16 seconds worth of data. And when we process that data in MEscope, in the video wizard, what we call our wizard, it's a 5-step process. I won't go through that today, but that's where you want to initially look at your data from your video to make sure that you have data that matches up, the number of frames. Well, if you just take the recording speed at 60 Hertz, times the number of frames that the wizard shows you, that should match the time in seconds of the video. Or let me say it differently. If I multiply 60 times 16, let's do it really simple. 60 times 10 seconds, I would have 600 frames. So with 16 seconds, do the math, 60 times 16 seconds, I should have what, maybe 1,000 frames, close to 1,000 frames. So the second step in the wizard will tell you how many frames are in this video. And that's the first check that you want to make of your video to make sure that you recorded or that MEscope agrees with you. Let me just go down here and click on one of the Google phone. So here's a Google phone, and again, you can see that it's over a minute's worth of data here, but this has got the slow-mo buried inside. Well, it's 120 Hertz. You can kind of hear some different noises. I'm not sure that you can hear that in the background, but that's the raw 120. And then
Yeah,
I've
but-
got a whole bunch of projects that I've set up, because these videos, when we extract the time waveforms from each video, and that's what the wizard does, then we do the FFT of that, and we get the what's called a DFT, or a digital Fourier transform, the spectrum. And that's where we can see the frequency content of the video. So those are the three things we're going to look at here. If we open up any of these projects, well, we got two here, let's say for 60 frames per second of the iPhone. We're going to get into ODS FRFs in a minute, but let's just start off with a raw 60 frame per second iPhone. This is a project with the data in it, and if we don't do any truncation, we can truncate in terms of the number of samples and also in the number of pixels. So the processing time in the wizard is the number of pixels per frame, and as Sean said, the 4K, actually that is 8 million pixels per frame, times however many frames. Let's say in the case of the 60 Hertz, it'd be about 1,000 frames. So that's a lot of data to store in your computer. And depending on how new your computer is, it gets a little clunky to try to put all the data from these different videos into one project. So I've broken them up here, and you'll see that MEscope on my computer works quite well. Can open up these files with time waveforms, DFTs, and a window that we can display the data on. So we have 60, and then we got pixels, and then we got 120 for iPhone, and then we got 120 for pixel. We're not going to get through all this today. We actually, the pixel gets accurate 240 Hertz data, so I went ahead and calculated the ODS FRFs. We'll take a look at some of that, and then here's the raw videos. And then down here, I have a project where I've saved the ODS at three of the orders: the running speed, second order, which is twice running speed, third order, which is 3 times running speed. And we'll look at the ODS data that we've extracted from all these videos and compare one set of data with another using the MAC calculation. Now we have 2 correlation coefficients in MEscope that we can use, or in some cases we can even compare raw data, DFTs, ODS FRF around the peaks. But it's a lot easier to reduce your data down to just some ODS data. It's just easier to understand. It's easier to explain to your boss or the plant maintenance people, whoever has hired you or is paying you to investigate vibration in machinery. So we'll end up comparing ODS data with the MAC calculation, and we'll just see that's kind of a measure of how well all the results are going to correlate when we get done looking at these different recordings from the cell phone. We got 6 different recordings, 3 from the iPhone and 3 from the Pixel phone. So let me open up, I'll put this down and I'm going to open up MEscope here. So here we are. This is VES, a couple weeks old, the version. I haven't downloaded the latest, but if you have a license to MEscope, you can always go to our website, and if your SMS, your software maintenance and support, is current, that is, it hasn't expired. If you buy MEscope, you get the first year free, and then there's a charge for SMS renewal each year. And you can go to the website anytime and download the latest software. And I do the support now, and I just recommend to anyone who has trouble with MEscope that you use the latest version of the software, just like I have here. So we can do things together over the phone, over the internet, and I can help you get through some of the details. MEscope has over 500 commands in it, so it's not trivial, but it's like MS Word. MS Word, you know, a word processor, I only know 10% of the commands. I can get my job done with it. Same with MEscope. You're never going to understand all the commands in it, but you certainly need to know enough to get your job done. So over here, we got links to a lot of help. Our YouTube channel, the Vibrant website where you download installs for the new, the latest, and this is our latest version here, at least for this version. Your current release date is October 17th, so I'm a little bit behind. Technical papers, application notes, very useful to go through some of that. And the operating manual is right on in the software. So if I go up here to help, there's the manuals right there. So I know most engineers don't like to read manuals, and you just want to get through with your work and get things done, but it's right installed with your software. The license manager is the first thing I'm going to ask you about if you call or if you're having difficulty running your MEscope. Here's my license and I'm using. Here's another one that's not being used that MEscope can see on my desktop. We always recommend you put your license on your desktop. Now, MEscope will pick up that license and store it somewhere else on your computer. Don't worry about that. Just make sure you have it on your desktop. And then here's all the options. I like to say MEscope is like a food chain. So we got advanced signal processing, modal analysis, video processing. That option is what you need to process videos. So let's just go ahead and open up one of these. I'm going to open up the 60 hertz pixel. And we'll just take a quick look at that. This is,
we got someone's requesting that you expand your window. If you can make it a little bigger.
okay. I'm loading up this project right now.
Oh, okay.
And there it is, full size.
Okay, thanks.
All right. Now what we have here are almost 27,000 time waveforms. So those were extracted from frames of the video. The algorithm that we use in MEscope goes through frame to frame to frame and compares the motion of each pixel in the video to, well, the position of each pixel. So it's based on color variations. And of course, we take the raw video right out of the phone, which is typically color. And so these background areas here are not going to show us any type of vibration because the algorithm can't tell the difference from one frame to the next. There's no color variation. But we'll see here as we go on that we got a couple of spots up here where we mount accelerometers on the motor and then on the bearing blocks, the top of the bearing blocks. So we've done testing of this machine with accelerometers and compared it to videos. And I'll show you when we get to looking at some of the data that we're going to compare apples and apples. How does a video compare to between these different videos? But anyway, this is a lot of data. Down here are the DFTs, so I've got the same number. I always have the same number of DFTs as I have time waveforms. And that's because these are just basically the FFT, and that's built right into MEscope. So I can animate out of time or frequency. Let's just start the animation here. And here's my animation source, which is called grid DFTs. That's the way they're labeled right out of the wizard when we process. So here we get an ODS. So anytime we are animating data from a accelerometer or in this case video, 27,000 DFTs, this is what we're looking at. Now, where is this data being applied? Well, something that's unique to MEscope is we use a point grid rather than the pixels. Now this picture has been cropped a little bit, so it's not a full 8 million pixels, but it's probably 6 or 7 million pixels. We're not displaying the motion of all those pixels, but we are displaying them. If I click here and go show the points. There's the point grid. So those are the actual points where we've extracted motion from the video. And so those are the points that we have the time waveforms. If I click up here, now I'm sweeping through the time waveforms. And as I've already said, each sample of a time waveform corresponds to a different frame of the video. So the software is actually putting the frames from the raw video on the picture. And of course, there's a little bit of averaging and interpolation going on using the pixels of the video to animate the points. Now, if I crank up the amplitude, we can see things a little even better here. So let me just do that. Let's go back down here. This is a little easier to see. And you can see the dominant motion here at the running speed of the machine, which is about 1,000 RPM. The motion, even we saw that in the raw video, but this is a mode. This is a mode shape dominating the ODS at 1,000 RPM. Now you can see the base moving around a little bit down here. The whole machine is just bouncing on its rubber mounts. So if I go up here and to the animation and increase the amplitude. So let's just do that. So now you can see the whole machine is just bouncing on its rubber mounts, and of course the rotors are going crazy because they have a lot more amplitude and kind of going off the screen, and the coupler itself. This is what the algorithm pulled out of the video. But the key points that normally you would be interested in if you're doing machine monitoring in a plant program with accelerometers are the 2 points on the motor. You can see that this end of the motor is moving quite a bit. There's motion of the bearing blocks, and they're pretty much moving around because the whole machine is bouncing up and down. Now, if I go to a different order, so what's this peak over here at 1600 RPM? Well, that's not twice the 1000 RPM. What's going on here? This is the second order of the machine, but it's aliased around 1800 RPM. So Sean showed in his presentation that if we sample it at 60 hertz, multiply that by 60 to get the RPM, that's 3600 RPM sample rate. Take half of that for what we call F max, which is the maximum frequency of the spectrum, and that is 1800 RPM. So this is the second order, and the ODS is correct, but the frequency has been wrapped around 1800 RPM. So you can do the math on your cell phone or whatever very quickly. Just take 2000, take the running speed, which is 2000, or 1000 times 2, and then subtract it from, well, first of all, subtract 1800 and then subtract that number from 1800 and you get 1600. So that's the second order. Over here is the third order. You do the same math, except now you multiply 1000 times 3 and wrap it around 1800. So the math is very simple algebra to get these. And so we're going to compare, when we move forward here, we're going to compare these three orders that show up very clearly from the 60 hertz video with data that we get from the 120 hertz and from actually the 240 off of the Pixel phone. Let me open up one of those and just show you, because those, we get the first three orders, 1000, 2000, 3000 from 120 hertz. Let's open that up. Nothing that we're looking for if we're just looking at the first three orders is alias around 1800. It's now we're talking about twice the sample rate. No, I don't want to save the results. Okay, so let's go get, here's 120 hertz from the iPhone. So the first time we looked at the Pixel phone, let's just go 120 hertz from the iPhone and see what that looks like. And then we're going to move on to the ODS FRFs and then comparing the ODS data from one video to the next. So even with this simple test with 3 different recording speeds on 2 different iPhones, just to kind of verify everything, you get a lot of data. And these time waveforms and DFTs, there's thousands of them. Now you can cut that way down, and that's what we do to calculate ODS FRS. So here we are. Let's start the animation. Okay, we're pointing at the grid DFT, so we're down here, and there is the running speed. Little different frequency, but you know, the machine was just running, and you can see the first mode there looks very similar to what we got at 60 hertz. This is, again, this is off the iPhone. Here's the second order at 2000. Now again, if I crank up the amplitude, show the points, you can see everything moving around. Let's just crank the amplitude a little bit so we can see things moving. You can almost see a second order bending mode of this rotor. Those are results you would never get with accelerometers because you couldn't instrument that. So, you know, an iPhone's going to show you things. There's a third order, getting more complicated. Let's go back to the first order, which is where the base plate is moving around, or the whole machine is basically bouncing on the rubber mounts. First order bending of these rotors. And, you know, there's some bending here in the shaft that you can see, but you can clearly see the motor bouncing up and down and the bearing blocks where we're going to look at the data in a minute with ODS FRS. So this is where you want to start your analysis. Again, we got 24,000 time waveforms, 24,000 DFTs, a lot of data. You can't do much more with this than maybe do a screen capture and verify that you got some good stuff here. Now there's other peaks in here. So what are these other peaks? What is this big peak here? Well, if you do the math, that's probably the fourth order of the machine that's wrapping around 3,600 RPM. Now we're not showing the 3,600, we're showing 35, but 36 is half of 72. This data has been sampled at 120 times 60. So whatever that number is, 7,200 RPM. And we're looking at 3,600 RPM as our F max. I think Sean showed those. And some of these other peaks, they could be a resonance at that RPM. Resonances will show up here too if they get excited. And as I've already said, the orders themselves, they are a linear combination of resonances of the machine at that frequency. And we would call that modal participation. The resonance is the natural resonance of the machine. And of course, you can see it very clearly in these rotors. And a little bit, look at the shaft out here on the end, it's kind of wagging its tail. So you see mode shapes from ODS data, and that's the whole idea of MEscope. Let's move on, and again, I can click up here, and this is going to do a sweep animation. And again, the only difference between the sweep and the dwell down here, if I click down here, I'm doing dwell at that frequency. If I click up here, I'm doing a sweep. Now we have other tools in MEscope, so I can just pull out the sinusoidal motion at this frequency into a time block and animate that. So that's for you sine testing guys that are very comfortable with sine waves. You can get all that in MEscope from the video because the video has recorded all the vibration of this machine, and I can break it down into frequencies and then I can do a sweep animation at each frequency, and I'll get a picture that looks like this, where each sample of time domain is a frame of the video, and the frame of the video is being laid on the point grid. Again, we have a point grid here, same idea, and we can just click back here and display the points. So there it is, and that's what the animation is doing. It's moving all those points around. And Windows is doing an interpolation job of displaying each frame of the video, 6 million pixels, if you will, on the point grid, and it's interpolating the motion between the points. So we won't go into that anymore. Let's move on to another. I'm going to open up a project where we've done the calculation of ODS FRFs for the 2 points on the motor and the top of the. Okay, so you can see I've got a bunch of them in here. ODS FRF for the 60 Hertz iPhone, let's go down and get the ODS's. Well, let's just do the iPhone right here. ODS FRS from the iPhone. I'm not going to take you through all the steps that I went through to do this. Pretty simple, pretty straightforward. Those are commands in MEscope that allow me to select points and then calculate the ODS FRFs for the selected points, and then so here are the results. Let's start up the animation. Again, I like to tell anybody who's using MEscope, you want to get to the animation as quickly as possible, because that picture's worth 1,000 words. If you got ODS data that looks reasonable to you, and I like to joke as an engineer, you want to know the answer before you get there. This is kind of the answer that we're looking for. We're looking at magnitude and phase at the running speed of the machine, 1,000 RPM, from some ODS FRFs. And how many did I get here? Well, I just got 4 points that I selected. You can see that we got the X and Y values of those points, and we've got the velocity. Now, this is another advantage of ODS FRFs. I could do cross spectra. I could do auto spectra. Now, auto spectrum from the time waveforms is not going to have phases like we're looking at here. This is complex magnitude and phase. The advantage of the ODS FRFs are that I have differentiated the data so that it's got the true velocity units, inches per second, in the ODS FRS. Now, I can't do that with cross spectra because the cross spectrum is two DFTs multiplied by each other. So the units of the cross spectrum are going to be maybe displacement squared or velocity squared. But an ODS FRF, it's got displacement units when I create them off of TWFs that have displacement units. In this case, we actually differentiated the time waveforms, and that's done with the FFT. In MEscope, we do the inverse FFT, then the forward FFT, and then we get units of inches per second. So all this data, and then I didn't talk about scaling. So in the wizard, what we do is we pick 2 points in the plane of the video, and here it's very easy. We pick a point here and a point here, and we enter in how many inches or how many engineering units, that is, length units, is between the two ends. I can pick any 2 points. I can pick 2 points here. I can pick a diagonal if I want, or I can lay a yardstick or some measuring device in front of the video when I record it, and then use that to scale my data. So that works very good. We've checked that out with accelerometers. Again, you have to scale your data even coming off of an accelerometer because it's just a voltage. But you can convert all this data into engineering units, and machinery people especially want to see inches per second. Maintenance people want to see, well, you can see that the motor here is moving around 1/10 of a IP, and it's got the most motion here on this front end. Back end's moving around pretty good, but mostly in a different direction. That's at the running speed. Let me go to the alias second order. Well, you just get a picture right away of magnitude and phase, and many machinery people will just look at the phase difference between the motor and the pump, or the motor and the gearbox in a more complicated machine. Let's go look at the third order. Now it says 400 RPM. Again, you got to do the math because it's all wrapped around 1800 RPM. But you can see how the motion changes so drastically. And here we got things moving in phase with each other. And, you know, in the horizontal, the X direction, everything is moving. The motor is 180 out of phase with the bearing blocks. Now I could interpolate this animation here and get the whole machine to move if I wanted to, but I just did a very simple, I cleared out all of the what are called the links, which linked the data to the model. This model has, I don't know, thousands of points in it. Remember, it's the grid points, but several thousand points. And I'm just linking the ODS FRFs for those 4 points in the X and Y direction to the 4 points that I selected from the raw time data. Now, if I click up here, this is the data that this is ODS data, and I simply saved it from the peaks. So that's the simplest thing. You can call that curve fitting if you like. It's not a true curve fit, but it's just saving the value at the peak. And we can let's put up a comparison display here just to show that the values of the data. So I'm going to animate a pair, and I don't want the TWS, I want ODS FRFs. And then over here, I'm going to animate the shape data for the iPhone, 60 Hertz. And let's just go ahead and see what that looks like. Uh-oh. Line cursor must be displayed in data blocks. Correct the cursor, yes. So it won't let me put up the band or the what I had was the peak cursor, but I've also got something turned on here that, well, let me just make this large so we can just look at things a little better. Okay, so we can't make it that large because I can't see my mode shapes, because what we have it turned, I've turned on another feature here where, well, let's just shrink things down so we can see better. Okay, here I can move these around. I can't, this is a little bug I'm showing you here that we can't move these over here, but we'll just, this is the MAC value between the mode shape and the ODS FRF. And you can see that when I click on the 1500, of course, it just moves and displays that. And I'm seeing exactly the same values and the MAC value between the mode shape and the ODS, or you can call it an ODS. I prefer to call them mode shapes. Yeah, so there we are. Now, let me just see if I can get these to display properly here. Okay, so there we go. So if I click on the running speed, I'm looking at the data. Here I'm looking at the shape data. And over here I'm looking at the ODS FRF data. So very clean stuff. And we've done spectrum averaging from the time records, and that cleans things up quite a bit so that you get some very, very nice results. All right, how are we doing here? I'm gonna close that, open up a new project. And this project, we call it Shootout Shapes. This is where I've saved all of the ODS shape tables from the different videos. Oh, I just got the 120s. Oh no, here's a 240. Now this is the pixel. So we're just going to compare shapes now using the MAC calculation. And you can see these shapes all have 8 degrees of freedom, and then there's an envelope at the end that won't be used because it'll only look at the DOS of this shape versus let's say the DOS of this shape down here, and it's only going to look at you can see the reference is the same. I had to choose a reference to compute the ODS FRFs. So 3Y is on the motor in the vertical direction. The points were numbered 1, 2, 3, 4, starting at the outboard point or the outboard bearing block. And so I went 1, 2 for the bearing blocks, and then 3, 4 for the 2 points on the motor. Those points in the grid are numbered in the thousands because there's thousands of points in there. So if we're going to focus our attention on just a few points on the model, we want to number those points so that we can compare from one video to the next all the mode shapes, or in this case, ODS. So you can see we got every one of these has got the running speed around 1,000 RPM. It's got the alias ones are going to be at different speeds, but the 120s, well, let's just go to the 120s because these are, here's the 120 pixel results, and here's the 120 iPhone results. So let's just look at those because those weren't aliased. I'm going to display the MAC value for those. Okay, so I clicked in the pixel spreadsheet. I want to select the iPhone spreadsheet. There it is. Let's make this a little bigger so you can see. So this is comparing unaliased. This is comparing right off of, we saw the 1,000, 2,000, 3,000 of the ODS FRFs, and here's the worst case, 95%. So modal assurance criterion goes from 0 to 1, and anything over 90% is a very good correlation. So the third order running speed, you can see these are shapes 1, 2, and 3, and here's the pixels on this direction and the iPhone in this direction. And you can see that we're at 99. So basically the iPhones are getting exactly the same answer. Let's shut this down. Let's go get, let's do the same thing for we'll go with the 60 Hertz iPhone. Now these are going to be aliased. You can see the frequencies in here are aliased, but the shapes are also aliased, just different frequency. And you can see over here, here's the pixel. So let's just click here and then display the MAC values. And I'm going to pick the 60 Hertz or FPS pixel data. Bingo. Well, the second order didn't correlate very well for some reason. The running speed, 97%, very good. The third order, 99%. So just like with the 120, now these are the alias frequencies, but we just took the peaks on the ODS FRFs and saved those into these shape tables. Can I explain that? Not really. Is it an error in my data? Perhaps. Let's go and look at the 240. And again, we just pulled, actually the 240, if I go back and show you the raw data, it's got orders all the way out to the 7th order in the raw DFT data. But let's just click on this and compare its first 3 orders with some of the other ones, MAC value. So let's just compare them with the 120 pixel and see. Okay, well, we got 2 of the 3 orders matched up pretty well, 96%, 93%, and then these, there's no correlation there between the other ones. Let's try one of the iPhones. So just from going through the analysis of the 240 Hertz pixel data, Sean brought it up and we kind of confirmed that it's pretty good stuff. Let's look at the 120, or let's just go down to the 60. Let's just go 120. They got all kinds of combinations. Okay, very similar thing. 96%, 94%. Anyway, Mark, that's pretty much it for my presentation. Do we have any questions?
No questions at this time. If you have some questions, go ahead and get those typed into the question box there, and we get those answered for you.
This is being recorded, all of this, so it will be on our YouTube channel in a few days. And you can go back over it. So if there's no questions about what I showed, hopefully it was both Sean and I did a good job.
Yeah, I guess, in summary, they're both great phones. They both do a lot of great things. I think there might be a slight edge for the Android, if we're being honest, right?
Yeah, I would agree with that. With the Pixel specifically, obviously there's other Android options as well, but the Pixel Pro seems to be a little bit more accurate.
The Pixel Pro.
Yeah.
But here's the comparison at 120, where nothing was aliased. We just did straight calculations of ODS FRFs and saved the 3 peak values, and the iPhone and at 120 hertz, they matched up very well.
Wow. Yeah.
Third order, 99%. So we're getting it. And this is a magnitude and phase comparison. These are complex shapes. Let me just show you. Let's just go here. Here's the 120 pixel. I'll make this large so we can just look at the data here. Just a bunch of numbers. These are in inches per second. Here's the units. Here's the DOF. So the Mac calculation is comparing just what we call the roving, the 3X, the 3Y. Now 3Y, because that is our reference, you can see that its phase is 0. It's relative to itself. But the phase of all the other points relative to 3Y is just some number. And we saw that when we animated the ODS FRF data and the shape data, that they matched up completely at the peak values. So this is, what.
Go ahead. I just said we got a question in here. I didn't want to get answered, but go ahead and finish your thought there.
Well, it's all very simple math. It's very simple in the way that you want to take video data and end up with some ODS data like this. And what the Mac value is showing us is the correlation between 2 sets of shapes, magnitude and phase, and each one of them gave us, if I go to the 60 hertz, we didn't get a very good correlation for the second order, but first order and third order came out perfect. Can I explain that? No, I don't know what the difference is between the 60 hertz iPhone data, which was alias around 1800, but that doesn't affect the shape. That just affects the frequency and the 120 pixel data. So
we got one question in here.
Good.
And this might be for you, Sean. Have you encountered errors stemming from automatic image video processing that occurs on the iPhones?
Very fair question, and that may be the cause of it. I'm looking deeper into ways to edit that, and I'm going to put together a tutorial. You actually have to turn off quite a few things in the Pixel as well that are kind of on by default, and you got to do a little bit of deep dive into the actual camera settings themselves, so you get a little bit into there and turn off a lot of things. But both of them, obviously, the features that they sell, to their general customer is for cinematic presentation, or so they have built-in digital motion stabilization, which obviously affects the raw video, which we're trying to get out. So in the Google, you're able to turn all that stuff off, which is fantastic. And I think definitely gives the Google phone the advantage. there shouldn't, when you go through and you turn everything on the iPhone off based on all the documentation that I've found and the communications I've had with people at Apple, there shouldn't be any artifacts or digital stabilization that's still affecting it afterwards. So again, I'm going to put these tutorials together. I can't say for a fact, you know, 1,000% that there isn't still something affecting it, but you know, based on comparisons with accelerometers and stuff, they're awfully accurate. And I'd say that the Google is a little bit more accurate, but I'm going to put together multiple documents and hopefully be able to show you all that and compare directly to accelerometers as well.
Yeah, it might be a good follow.